Okay, so I'm going to have to untangle some variables here. This is number 35 in 14.3, which gives me these two formulas. Capital T is 2 pi the square root of L over G, and L is L naught times the quantity 1 plus alpha times the quantity T plus T naught. Okay, so hang on, I got to do all the bits and bobs here. So T is the period of oscillation in seconds of a clock. Okay, period of oscillation. Right, so someplace here there is a clock, and that clock has a pendulum on it, and the pendulum is swinging back and forth, right? And that causes the clock to tick. Yes? Everyone believes that clocks used to be made this way? Okay. All right. G is the acceleration due to gravity. Okay, good. That jives with my usual. L is the length of the pendulum.
That was kind of confusing to me too. It says the length of the pendulum depends on the temperature.
Yeah, so this is a length, right? And then that pendulum is made of metal, right? And so the warmer the metal gets, the bigger that chunk of metal is. You guys know that about metal? It stretches and contracts based on temperature. Okay, most things stretch or contract based on temperature, but metal does it really noticeably. Like for instance, this is why there's sag in telephone wires. Because if it gets cold enough, they can actually pull hard enough to pull them off the lines if you stretch them tight. Fences explode in the winter in Montana precisely because they do this on purpose, right? Like on a hot summer day, you stretch that fence, and there's actually a thing called a fence stretcher that you use to do this. It's like a big scary clamp. So you stretch this fence and then you tack it down to the fence post. And then in the winter it gets cold and the metal gets shorter. And so it pulls on the fence post. Normally that's nice because it keeps the fence post from, or the fence from falling on the ground. But if it gets cold enough, it snaps. So in the spring you go around and check the fences. You walk around and look for all the spots where either a tree has fallen on it or the cold just snapped it.
One of our fences, like, it looked like someone cut through it, but...
Yeah, sometimes they just snap because the temperature changes.
Okay.
Sometimes people cut through them because they want to drive the four-wheeler on the other side. Whatever. So we have this L, and L is itself a function of temperature. That's this thing, right? And what's the T naught doing in here? Let's see. So they told me L naught is the initial length. Oops, and I switched to using black for some reason. So L naught's the initial length, right? What's T naught?
The initial temperature.
Yeah, right? That's like the calibrating temperature. That's the temperature it is when it's L naught. You guys all see that? Okay. Alpha is, what did they tell you?
Some constant.
Yeah, some constant. Yeah, that's some kind of built into the clock thing.
That'd be like just the shape of the rod and stuff. Probably like a metal constant.
My guess is that's probably actually more to do with the gear ratio of the clock than anything else. But oh no, this is the length of the pendulum. So no, that's nothing to do with the gear ratio of the clock. That is absolutely to do with the metal that the clock is made of. Okay, and then this T is...
How much you got warmer or colder?
Yeah, that's how much off of T naught you are, right? So that's how off of T naught the temperature is. Okay. Now, what in the heck am I supposed to do?
It's asking how many seconds a day is a clock gain or lose when the temperature is T naught plus delta T?
Okay. So if they put a delta T in
Wait.
here, how does that change the... So really that's thinking this, right? That's thinking if we go from...
For the, it's T minus T zero. Or T naught. Yeah.
What?
Minus,
Oh,
not
yeah,
plus.
you're forming
And T
difference.
just refers to like the
Oh,
absolute
minus.
temperature.
So I lied.
Yeah.
It's not T plus T0, in which case this would be the amount of temperature off, right? It's
Just temperature.
just T, which is just temperature. You guys all see that? Sorry, my bad. I would like to defend that with, that would have been a valid formula, but probably would have had a different answer. Okay, so then they're wondering about how much does this thing gain or lose when the temperature is T naught plus delta T, right? Okay, so that's putting in here a delta T, right? You guys see that? If so, I think if T is T naught plus delta T, that really means that T minus T naught is just delta T. You guys all see that? Okay, so how can I approach this?
That was my big hang up.
What's that?
That was my big hang up. I didn't know how to approach it.
Yeah, totally. There's a bunch of stuff here, right? So here's what I remember. I remember that this thing, right? Like some value plus a change in thing. That conjures up an idea in my head about maybe I should be thinking this is a DDT kind of thing,
Okay.
right? Like if you're changing that thing a little bit and you want to know how the other thing changes, that's really what a derivative is kind of for, right? So that might clue me, yeah, I got this problem though. I can't actually do hard derivatives, right? Because what am I even trying to differentiate?
T and T naught.
Like which function am I trying to figure out how changes?
You want the period oscillation.
Yeah, I'm trying to figure out how many seconds this thing gains or loses a day, right? That's like in that capital T thing. You guys see that? Okay, so I need to figure out, like, maybe I want approximate change in capital T for change in little t, right? Like that's kind of the idea I'm shooting for.
Could you substitute that T for that L in the pendulum?
Oh yeah, that's probably a good idea, right? Like right now this doesn't even seem like t depends on that little t, right? Capital T seems independent of little t. Why isn't it?
That was a function of little t.
Yeah, little l is a function of little t, right? So one thing we could do is we could eliminate the L variable. You guys all see that? What's that?
You would still have an L naught, though, right?
I would still have an L naught, but what's L naught?
It's like a number.
Yeah, it's just a number, right? So it's constant. So we could maybe do this. We could do, well, let's make us a function, capital T as a function of little t, right? And that's going to have, oh, maybe I should leave myself some space here. There might be another variable in there, right, when I'm done? Let's see if there is. So I got a 2 pi, that is constant. And I got here a square root of something over g. What's g? Constant.
So let's try some constant.
And on the, yeah, that would be 9.8 meters per second squared, assuming you're doing this math in, assuming you're in the metric system, right? If you measured the length L in inches, you probably want to convert. Right? The 32 has feet on it.
Okay, never mind.
Just convert everything to meters. All right, so the L though is L naught plus alpha L naught. Sorry, I did a little distributing here. Times T minus T naught as a quantity, right? Is there another variable in there?
Alpha is some constant, okay.
So alpha is a constant based on the clock, right? G is a constant based on the world. T naught's
Temperature change.
the initial temperature, right? So that's also a constant. L naught,
Also constant.
also a constant. Oh, so this isn't even a function of two variables, right? This is just L is a function of T, right? Or sorry, capital T is a function of little t. Thank you for catching me. You guys have not caught all of my misspeeches. I had to make two little
T is a
blah blah
function of
blahs
T.
in the description of video. So, what do you need to do here now?
We'd be taking a partial derivative of t.
Yeah, except it's not even a partial.
Yeah, it's just derivative.
Just take the d dt, right? So get capital D, capital T with respect to little t, and you get 2 pi
1/2, all of that, so negative 1/2.
Yeah, so this is what, a bunch of function of t, right, under square root. So what do you need? You need to
1/2,
bring the power down, 1/2, good.
and all of that to negative 1/2.
All of that, so all of this to the negative 1/2 power times derivative of the inside, which is, see, that crap's a constant.
Branches.
So what do you get?
Wait, no, not branches.
Just
How about if I write d dt of, let's see, I've got L naught over G plus alpha L naught over G times T minus T naught.
okay, that makes sense.
Does that make things a little easier?
Then it would become a 1, all that. Two constants, t and a 1 variable.
Let's see, so I think I got a pi and a L naught plus alpha L naught T minus T naught over G to the minus 1/2 power times alpha L naught over G, seems like.
Why would you keep that, but not the L naught over G? Because A is a constant. If that's a constant, that means that would all be a number, just like L naught over G would just be a number.
Okay, so let's see. This piece, right?
Oh, okay.
That's a number,
Yeah.
so that's going to zero out.
And then it would be a number times.
And this is a number times t minus this crap times a number. You all see that? So I just end up with this coefficient here. All right, now, Now I feel like I screwed something up, but only because they told me that this was supposed to be independent of L naught.
Oh, can we shift? So we know. Oh, wait.
So we can make some manipulations here, right? So let me show you manipulations, and then we'll see if we can figure out where I'm seeing a problem in my head. So this is a negative 1/2 power, right?
Yep.
Which means
It's below it.
I need to flip it over and then put it in the square root, right? You guys all see that? So that's really me thinking about negative 1/2 as negative 1 times a half. So I'm going to do this power first and then that one. So I'm going to get the square root of all this crap flipped over. So let me write that as, wow. And I'm gonna rewrite this stuff factored out. Because I think what I'm supposed to, oops. I'm gonna rewrite this crap factored out, but I'm gonna actually factor it, right? And there's a times alpha L naught over G. You guys see this?
That whole quantity is to the -1/2, so it should be 1 over that whole quantity in the square root.
So I flipped this whole thing over.
You can't, because the whole thing is to the -1/2 power. So
Yeah.
it should be 1 over that whole thing in the square root.
Uh-huh. And then reciprocate and multiply. So I did this. I did a over b to the -1/2 power, right?
Yeah.
Is a over b to the -1 to the 1/2.
Yeah.
And then I flipped over to the inside and took the
Oh,
square
okay,
root.
never mind. That's not that. Yeah.
Okay, so let's see. I would really like to cancel the L naughts though, right? You guys all see that?
Yeah.
They told me this was supposed to be independent of L naught, and I would like to cancel them.
If we could find.
But-
something-
But why can't I cancel them?
Cause one's a
One's to the
square
one
root
and
of
a half,
one.
one's to the.
Yeah, one's in the square root and the other one's not. So,
You'd square everything,
Right,
Um,
you get the same problem.
yeah, but
Okay, so
so
the-
if you square everything, you have to square both sides, right? And I don't want dt squared.
Yeah.
But we could fix that. We could square root both sides.
Put them in the same.
But then we're back to where we started, right? What's up, Josh? Okay. What
Yeah,
did I
so-
screw
so
up?
The trick, no, you didn't screw up anything. There are two tricks. One trick to, obviously that's gonna work, but it's easier if you take the L naught and the G out of that, you know.
Yeah, so
Before you
certainly,
differentiate that, you know, so the way I did it, I just said, T equals 2 pi times the square root of L naught divided by G times the square root of 1 plus, alpha times T minus T naught.
yeah, certainly.
And then I differentiate it, so that makes your life easier if you do it that way, but obviously you can do it that way.
So,
Where-
hang on, let me get to there, and then, so, you guys see this? She's saying I probably could have made my life easier at the beginning here, right? By taking the constant that I had multiplied by a bunch of junk out of the square root and just writing it as a separate constant. You guys see that? So, right here, that would be, this crap is constant, right? That G over L naught. And so I could pull that out and write this thing instead as pi times the square root of G over the square root of L naught times alpha L naught over G times the square root of 1 over 1 plus alpha T minus T naught. You guys all see that? And then I can obviously do a little bit of canceling, right? And so all told here I'd get pi times the square root of L naught on the top and the square root of G on the bottom and an alpha out front. And then I've still got that square root of this 1 over 1 plus alpha times T minus T naught thing. You guys all see that? Okay.
So you want to get rid of that L naught. And the way you do that is when you start considering that what that's giving you is how many seconds you're off in each period. But what they're asking in the question is how many seconds off you are in a day. So you have to, in order to get the answer, start considering how many periods are there in a day.
You guys see that? This is the change in the oscillation period, right?
Yeah. So every period you're off by that much. What they're asking is how many seconds are you off in a day?
Yeah, you guys see that?
Do we know how long a period would be for this one?
Okay, so let's see. They tell us, right, that T, the oscillation in seconds of a pendulum clock, right? Okay, what does that mean?
Means that T would be a period.
So let me maybe do a little dimensional analysis, right? T is a number of seconds, right?
Like seconds per period.
Yeah, exactly.
Right? This is the number of seconds it takes to get one period done, right? And we've said, okay, so dt, right, is the seconds per period per, yeah, per some kind of change in temperature, right? So maybe if I write it as seconds per period divided by, what's a temperature unit? Yeah, degrees, right? So the units on dt are going to be seconds per period per degree. You guys see that? Okay, but I really need to know how many of these periods go into a whole day, right? You guys see that?
Solve for T first, right? And multiply whatever we get T for to be 24 hours.
Yeah, there's some kind of horrible conversion here that I frankly don't want to play with. All right, let's see. So what's our horrible conversion? So a period is a clock tick, right? You guys all see that? So in an ideal clock, right, there would be how many seconds per period? One, right?
Yeah, but this is an ideal clock. It's changing all the time.
Yeah, and so this clock is off by a little bit, right? And the amount it's off when I change to a small when I add some number of degrees, right, is that crap times the number of degrees we added. You guys all see that? Right, because I want to do seconds per period. And then I need to divide this into the number of periods it takes in a day. And so there's some disaster here, and I don't know what it is. Frankly, I don't want to play anymore. Okay, so let me shut this off and let's see. Okay, so the camera died earlier, and I'm going to splice on to the end of this thing with ticks and time the rest of the answer there. So I think I ended off with this d capital T, d little t is alpha pi, and then there's like a square root of L naught over a square root of G, and then there's like a square root of 1 over 1 plus alpha times T minus T naught in there. And then we had this other formula that we knew for capital T. So let me say this. There should be something like the number of ticks per day, right? And this number of ticks per day should be the number of seconds in a day, so 60 squared times 24, that's seconds, right? Times 1 over t, right? Because t is the number of seconds per tick, right? So think about t as seconds per tick, right? And this is seconds per 1 day, right? So that seconds cancel, right? And 1 over ticks is ticks on the top and days, so we get ticks per day, right? And in an ideal world, t is 1, right? And so this is just the number of ticks per day is 60 squared times 24 seconds, right? Great, awesome. But we're dealing with this thing where it's kind of annoying and not quite. So in total, right, the lost or gained time, right, in seconds, is going to be the number of ticks per day. So that's this thing. So 60 squared times 24 over t. Right, and the units on that whole thing is ticks per day, multiplied by the error, right? That's my d capital T, d little t. So that's that thing. And really, we should have to evaluate this somewhere, right? And so we're going to be evaluating this thing at t plus delta t, or t naught plus delta t, right? And then we need to multiply, because this sucker, right, d capital T, d little t, has units of seconds per tick per degree, right? Because it's the derivative with respect to temperature of this thing that has units seconds per tick. So I need to evaluate that thing, and then I need to multiply by how far we went, right? So I need to multiply by delta t. That's how far we went in the change in temperature direction, right? Okay, so if you plug all this crap in here, you get that the lost or gained time is 60 squared times 24. And then I need to divide by t. So I've got this whole formula someplace for t. And it's got a 2 pi, the square root of L naught over g. And this is manipulated just a little bit. And actually, I'm lying to you just a tiny bit, but I'll tell you why later. So I've got L naught over g under square root, and then I have 1 plus alpha t minus t naught in that square root. So that's all of capital T there. And then I've got multiplied by that, my derivative information. So I've got an alpha pi square root of L naught over square root of g. And again, that's a little bit of a lie, but whatever. And then I got this square root of 1 over 1 plus alpha t minus t naught. Right. Oh, and I really should have to evaluate. Let's see. So I need to evaluate both of these things at t plus delta t, right? Or t naught plus delta t. So these guys here are a little bit of a lie too, but I'm just giving you the idea. So I'm going to let you guys straighten out exactly how I lied to you there. You have to evaluate those somewhere appropriate. Probably actually this one. Right, that should be the number of ticks in a usual day, so that's when t equals t naught. So this guy you can do a little bit better, right? This piece actually should be 0, so this piece should just be 1. So, and then this guy, well, that thing's a delta t there. Okay, so I didn't lie to you, I fixed it. Okay, and then we need to multiply by delta t. And then we should notice that there's one of these guys, right? Let's see, there's a pi on the top and bottom, great. There's a 2 on the top and bottom, so you can slash that a little bit. And then there's one of these square root of L naught over g's on the bottom, and another one on the top there, so those can cancel out. Okay, so all told out of this, I get 60 squared times 12 over the square root of 1 plus alpha delta t times delta t. So there's your total amount of lost or gained seconds per day. And I told you I was lying to you a little bit when I said about these square roots, and I really was. And the thing I'm lying to you about is I'm no longer sure whether these are lost or gained seconds. The reason I'm no longer sure whether they're lost or gained seconds is I've been playing this game a little bit, right? Like, I had L naught over the square root of L naught at one point in the other first version of this talk. And I thought about that as square root of L naught times square root of L naught. over square root of L naught, right? And I canceled one of these. That's totally fine. Except for freaking gravity, right? Because gravity should be, well, that's like 9, and earlier when I said this in class, you all were like, oh, it's just 9.8 meters per second squared. It's fine, like, don't sweat it. Well, it's 9.8 meters per second squared down, right? So probably that G has a negative sign on it, maybe? I don't know. I'm not a physicist. And I don't know whether they took that into account when they wrote the formula or not. And so my guess is probably that's taken into account. Probably you don't need to worry about it. But you really should sweat this when you're doing this, like, oh, well, like the square root of whatever squared is the square root of whatever quantity squared is the thing, right? Because these aren't actually equal. None of these are equal to one another. These are all slightly different functions of this little squiggle, right? So you have to be a little careful, and we haven't been. But this is where the L naught went, right? It canceled because we had to account for the number of ticks per day.